Okay, I want to talk a little bit more about IP networking. So again, this is additional information of what I covered in the lecture. Um, Another viewpoint, another way to look at it. Okay, so the internet is actually a network of connected networks. So I'm going to show a local area network here with just a couple computers. I'll call them nodes. Okay, and then typically have a router. I'm going to show them just as a ring. That's how they're often depicted. We may have a couple of hundred connected nodes here. Again, there is usually not in a ring topology. There's usually a direct connection between each of the host computers and the router. The router will typically have multiple, um, may be connected to several different networks. For example, like this, although this is a little bit uncommon, what's a little more common is actually to be connected to perhaps a network of other routers. That are connected to other networks. And for example, we talked about IP addresses 192.168 dot 20 sorry dot 0 no the 20.0. So the corresponding net mask here would be 255.255.255.0. So this is a 20. So all the hosts in here would have to have 20 dot maybe 10, and this one would have to be 192.168.20.15. The router would also have to have an IP address, and it would have to have an Ethernet card or a network adapter connected to each of the, in this case I show it connected to 3 different networks. It would have to have 3 different IP addresses, one on each of the networks, 3 different network adapters. So one on this, and then this network might be 192.168.30.0, 255.255.255.0. So all of these computers would have to have, can't use 0, that's the network address, and then actually you can't use 255, that's used for broadcasting. That particular IP address is used to indicate that you want to broadcast to all the nodes on the network. Then similarly, this would be 196.168.30.100. The router would also have to have here an IP address on that. And then here, this would be another network, this would be another network, and so on and so forth. So every computer or host has a unique IP address. Again, the IP address is divided into network and host parts. To get assigned an IP address, you can do that 2 ways. That can be set up by the administrator. That's called static assignment, or dynamically by what's called a DHCP server. So that would be a special computer on the network whose responsibility, DHCP, whose responsibility is when the computers boot up, they make a broadcast on the network saying, I need an IP address. Is there a DHCP server who can assign one? And then the DHCP server says, here, this one's available, hasn't been used on this network yet. You use it. Okay. It also gives back not only the IP address and net mask, but also the IP address of the router or gateway, and also the IP address of a domain name server, which is out here on the network, on the internet somewhere. Okay. Routers are used to connect networks, and they're connected to multiple networks and have IP addresses and interface cards on all networks. Now, a particular host can tell the IP if the IP address of a destination is on the local network or on another network by looking at the destination address and using its net mask. So if it sees that the destination address is on the local network, on the same network, let's say this is the source and this is the destination, and the source wants to send up data to 192.168.20.15, it says it can look at that with the net mask and say, hey, that's on my local network. I can talk to it directly. Okay. If, on the other hand, it's 192.168.30.10, this computer is the destination. This computer just says nothing more than, that's not on my local network. I'm just going to hand that off to the router. Okay. And so it gets the local MAC address of the router, sends it to the router, then the router's responsible to making sure that the packet goes on then to the next network or another router if it doesn't know how to get to that particular network, and then the packet's just passed on through a series of routers until it reaches its final destination. DNS. I have a DNS server here. I've mentioned that humans typically refer to hosts by names instead of IP numbers. When you type a host name into your CS server.evansville.edu, first thing that's done is that's actually translated to an IP address. Let me bring up actually a command window here. Okay, and if I ping CS server.evansville.edu, I don't think CS server is actually set up to respond to pings, but so I don't get a response back. It says request timeout, but this is the IP address of CS server on the internet, 192.195.228.35. And indeed, if I can remember that, let me bring up a web browser. Fit this on my little screen here. I'll pull down this. I can actually, instead of referring to CS server by name, I can actually type in http :/192.195.228.35 and get to CS server directly that way. This is the main page on CS server. This is the same page I'd get if I typed in http CS server http / CS server.evansville.edu. I'd get the same page, but in that case, my web browser would actually first have to contact the DNS server and get the IP address, and then address the request for a web page using that IP address. Okay, let's see. Where was I? Here we go. I'll also mention, let me actually erase the page here. That on your computer actually has a couple of different IP addresses assigned to it. And again, you can find out information by typing in Windows, it's ipconfig/all. under Unix, it's actually ifconfig. So I have the IP address of this computer on the internet. It's 192.168.1.3. I'm working from home instead of at the university. Let's see. Doesn't give local host information. There is another IP address that every computer has assigned to it, and that's 127.0.0.1, and that's on a virtual 127.0.0.0 network. What this allows you to do is to write networking software that communicates to your own computer using network communication software without even having a physical network adapter available or being connected to any network at all. So it's a nice thing to know that you can develop network software even when you're not connected, and test network software even when you're not connected to a network. I've already mentioned on the net burner, we're going to actually set it up so for our computer we'll use an address of 192.168.17.1 with a corresponding net mask of 255.255.255.0. So the first 3 bytes will form the network portion of our local network, and then what I suggest for the net burner is just to use .2 with the same network address. Okay. On Ethernet, so the TCP/IP Internet Protocol works regardless of how the computers on the local network are connected physically. And the most common networks in use today are either wired Ethernet or Wi-Fi. Packets on the local network are Ethernet packets containing Ethernet addresses of the source and destination, or MAC or hardware addresses. And then ARP is used. It's another protocol to translate an IP address into a MAC address so that we can do that communication over the local network. TCP takes care of, so IP takes care of routing the packets by address. That's the networking part. TCP allows you to have multiple connections between the same 2 computers, right? You might have, for example, on CS Server, you might have a couple of SSH sessions open. You might have a couple of tabs on your web browser open, all connected to CS Server. In that case, you'd have multiple connections, simultaneous connections to the same IP address. So TCP is the layer that sorts that out, okay, using different what are known as port numbers to the same, and these are virtual ports. They're not like a hardware connected port, but port numbers to sort out the different streams of traffic between the same source and destination. So IP packets contain not only the IP numbers of the source and destination, but also the source and destination TCP port numbers. TCP also takes care of error detection and correction, and that's done automatically for us. We don't have to worry about that at all. So ports, and then also takes care of errors for us. Okay. We don't have to worry about that at all, which is a nice feature. So when you make a request to a computer, when you connect via TCP, you not only specify the IP address of the destination, but you also specify a particular port that you want to connect to, because the web server on the destination is listening on a particular port. I think HTTP actually uses a port number of 80, and you can include this in the destination address in your web browser. You can request specifically a connection to port 80. You put :80 after the IP address. Okay. Now, if you try some other port address, there's probably not going to be a web server listening there. Sometimes you'll see web servers that are configured to listen on other ports. That's kind of common often these days to set up like printer servers and things like that. Some other common ports, FTP. So this is the port you want to specify that you're connecting to. Your source computer is sending data out a particular TCP port, and then the server will communicate with that port. It's a completely different port number. Actually, these port numbers or service numbers that are below 1024 are considered privileged ports. So those are where various server software that's running on your computer listen on these particular ports, and you have to have administrative privileges on your computer to actually even set up programs to listen on these ports. Secure Shell, one that you've probably used, listens on port 22. Telnet's 23. Again, that's kind of obsolete, as is FTP. Simple Mail Transport, SMT Transport Protocol is port 23. Okay, so what are known as secure or well-known ports have port numbers under 1024. UDP is similar to TCP, but no error correction. There's no guarantee of even packet delivery. It's primarily used for streaming services. We're going to concentrate mainly on TCP. Okay. And then at the programming level, the most common API for doing TCP/IP networking is known as sockets, and this is used in all three major operating systems. So Unix, Macs, and Windows use the sockets API for communicating, sending data over the internet between source and destination. And sockets provide support for both TCP and UDP. It's a general API for inter-task communication. In addition to TCP/IP or networking sockets, you can also create what are known as local sockets, at least on Unix systems. I don't know that Windows supports this for communication between processes running on the same computer. So this is the programming API that is commonly used. Okay. So a couple other things. Yeah. Name to IP resolution. I mentioned DNS servers are used for that. Another way is there is a file. It's called the etc host file, and it resides in the /etc/etc directory and on Linux computer, and it's just a text file. And you can actually enter your own mapping between IP addresses and names in this particular host file. And again, that's not commonly done anymore. We might do that to actually set up a mapping between a name and our NetBurner board if you want to do that, so that we could refer to it by name, and then it would actually get the IP address from this host file. This is in a different directory on Windows. It's buried down in I forget, Windows System 32 etc something like that. but Windows can also use this host file. And then a mapping between IP and MAC address. That's, again, ARP is the protocol that's used there, and then typically if your computer needs to communicate with another computer on the local network, sends out a broadcast address saying who has this IP address, and then the destination actually responds. There is an ARP command that you can use to look at, I think, hardware addresses and IP addresses on the local computer. I think they're corresponding to the host file. There's an ethers file that's that you can use to do this mapping, but then that's obsolete. It's not recommended. IP assignment, we've talked about that as well. You can do that statically, or again, more common is DHCP, but we're going to use static assignment with our net burners. Okay. The other thing that you'll run into with the study of networking is what's called the OSI model, or the 7-layer model, and then for networks, TCP/IP actually uses a 4-layer model, but the first layer is called the physical model, and Ethernet resides here. This is the Ethernet, at least physical layer. Ethernet kind of encompasses 2 layers, and these are the specifications on, you know, the connectors, 10 base T, 100 base T, you know, different types of wiring and connectors here that live here. You know, Wi-Fi is also included in this layer. Then there are others, you know, local talk. You can also use serial and parallel ports, USB, Bluetooth, DSL. All those have, you know, corresponding layer 1 levels. Layer 2 is the data link layer. So this is actually specifies, you know, the format. I think in the physical layer are the voltages that are acceptable on the wire. In the data link layer, it's actually the maximum length of the packet, you know, the format of the packet, what's in the header, you know, where is the MAC address placed in the header, you know, Wi-Fi, PPP, SLIP, token ring, frame relay, they all exist in this layer. Sometimes you'll see a 2.5 level layer for network topology, and this is where at least ARP would live. Otherwise, I guess it would be placed down in the layer 2. It's kind of this mapping from the networking layer down to the Ethernet layer. Layer 3 is the network layer. This is, you know, IP version 4, IP version 4, IP version 6, which we're transitioning to. There's some other ones, Apple Talk, IPX, that are largely obsolete now, but it's this layer that determines how packets get from the source to the destination, how that routing takes place. And then layer 4 is what's called the transport layer. This is where, you know, TCP and UDP, and then again there's some obsolete ones, SPX for non-TCP/IP networks. Again, this actually takes care of, you know, multiple streams, different ports. Also, you know, any error correction can be implemented, whether there's actually a connection-oriented service for TCP or not for UDP. Layer 5 is called the session layer. Okay, again in the OSI model. So, I don't know, I guess sockets would live, the sockets API would kind of exist in this layer. And then there are some other network services, NFS, which is the network file system that's used on Unix, or SMB, the network file system that's used in Windows, would uh, live at this layer. Layer 6 is the presentation. And I think in that layer, the best modern analogy would be, what's TLS stand for? Transport layer security. I don't think that's correct, but this layer can take care of security between endpoints. And finally, in the OSI model, layer 7 is the application. And this is where we have like our HTTP, secure shell, DNS, DHCP, FTP, Telnet, all those live in this layer. Kind of in the this is what's known as the OSI model. In the TCP/IP model, it's generally thought of as being a 4-layer model, where we have the application layer, which encompasses 5, 6, and 7. The transport is layer 4. The network layer is layer 3. And then the lower 2 layers are the physical layer, and aren't really specified in TCP/IP, but there's no prescribed physical layer. It's in the model, but it may be any number of different lower levels. But the TCP/IP model does specifically define the network, transport, and then different application protocols that are used. Let's see. I think that's it for, again, I just wanted to give you a little more detail about how IP networking works. I'm not sure if I've provided any help or not, but hopefully so. But it may help you remember a few things you learned in networking, or may provide a little bit of a background when you get into the networking class.